Last time we looked at the definition of Jacobi symbol, and more importantly we looked at these properties in blue. So there is this first property is that it is totally multiplicative, AB by n factors. Second is reciprocity law, and third is some examples of the Jacobi symbol. So what is 2 by n, what is minus 1 by n, and then based on these properties we gave an algorithm to compute the Jacobi symbol in an extremely fast way. So the algorithm is in green. First you check whether a and n are co-prime, otherwise obviously you factor n is composite. Then you, so now assuming that a and n are co-prime, reduce a modulo n, so bring the remainder around n by 2, magnitude less than n by 2, and basically then you replace a by n by n by a, okay, and then when you will again repeat, you will be reducing n mod a, okay. So every time n is getting halved, that was the main point, halving was the main point. So this is why it is so similar to Euclid's GCD algorithm, okay. Division causes the halving, and the complexity is O tilde log n. So it's a very fast way to compute the Jacobi symbol. Based on this, the first primality test was given by Solovay-Strassen. To design a test. So that is again the input is just a number given in binary, and you want to give a Boolean output, 0 or 1, false or true, right, whether n is composite or n is prime. So the first step is simple, you just check whether n is even, 2 divides n, or n is a perfect power. So check whether these a and b exist such that n is a to the b. If yes, then clearly n is composite. Output composite. Else you continue with the main idea, this computation of the Jacobi symbol. So you pick a random a, which will be co-prime to n. If it is not, then you factor n. And you compute a by n. Okay, you using this Euclid GCD type algorithm, you will very quickly get a by n, which is plus minus 1, and if this a by n is a to the n minus 1 by 2 mod n, in that case you guess that n is prime. Otherwise, if this congruence fails, then you definitely know that n is composite. Okay, so step 2 is very efficient. Step 1 and step 3, by repeated squaring, you can do it in around log square n time. Okay, so this complexity is log square n. So it's a quadratic time algorithm to test primality. Why does it work, right? So we have to now prove those claims. So first claim is the easy one, which is that if n is prime, then it outputs prime. If n is prime, then a by n is what? A by n is the Legendre symbol, and you know that it is by definition a to the n minus 1 by 2. So this is the easy part. This is clear. And second claim is the important one, that if n is composite, then the probability that you get an output prime over A's right. So over the choice of A, the probability that you get the wrong answer, this is bounded by half. Okay, so thus this is not a deterministic polynomial time algorithm. It is a randomized polynomial time algorithm. It is always correct on primes. It may make a mistake on composite. It may say that a composite number is prime when it is not. So the idea of the proof is you identify a subgroup and use the property that subgroups of a group cannot be bigger than half. So consider the set of bad A's so n is composite, and still there are these A's such that A by n is A to the n minus 1 by 2 mod n. Okay, so collect these A's, call this set the bad numbers, right, which are fooling the algorithm. First observation is that B is a subgroup of Zn star. It's a multiplicative subgroup. Why? Well, because if A is in this and A prime is in this, then their product A prime is also in this by multiplicativity. of Jacobi symbol. Okay. We will show that, so, well, since it's a subgroup, it means that the size of B divides phi n. So, either the size of B is phi n or it is less than equal to half of that. So, we need to show that B is not the whole set, thus B is less than equal to phi n by 2. Okay, so that will finish the proof. The size of B cannot exceed half of n. Okay, so bad A's are few. How do you show that B is not Zn star? So the idea is Chinese remaindering. Okay. So we'll do two things. First, we'll show that n is square free, and then second is we'll do Chinese remaindering. Suppose there exists a prime P1 dividing n, well, such that its square divides n. NB P1 E1 P2 E2 PK EK such that P1 to PK are distinct primes. So suppose a prime square divides n, we'll rule this out. Okay, we'll show that this can't happen. So this can't happen assuming B is equal to Zn star. Okay, so B equal to Zn star would mean that generator G of Z modulo P1 E1 star. Note that Z mod P1 E1 star is a cyclic group. It has many generators. So for a generator G also, this Jacobi test, Solovay-Strassen test passes, right? That is what we are assuming. This is also in B. So which will mean that G raised to n minus 1 is 1 mod P1 E1. In fact, we knew something stronger than this. We knew that G to the n minus 1 by 2 is G by n, but that is a sign, it's plus minus 1, so we squared it and we deduced this property. So which means that by the order of G, phi of P1 E1, the Euler-Taussian function, that's the size of the subgroup. This is equal to P1 E1 minus 1 times P1 minus 1, and this divides n minus 1. E1 minus 1 is at least 2. So this means that P1 divides n minus 1. And that's a contradiction. As P1 divides n. Obviously, it is at least 3. So P1 cannot divide both n minus 1 and n. That's a contradiction. So this contradiction means that that n is square free. So say n is equal to product of these PIs, distinct primes, okay, their multiplicity is 1, P1 to Pk. That was kind of the pre-processing part. So what we have deduced is that n is square free, so n has these k prime factors distinct. Now suppose there is a prime Pi and a number A such that, or let's call it G, and a number G such that G raised to n minus 1 by 2 is not the same as G over Pi, mod Pi. Okay, suppose there is a number G and an I such that G raised to n minus 1 by 2 is not the same as Legendre symbol G over Pi, mod Pi. So then I claim that we will contradict B equal to Zn star. How is that? Then what you can do is by Chinese remaindering theorem, CRT, you can find an A which is the same as G mod Pi and 1 for the other Pj's. Okay, this A will exist. Now let us check A raised to n minus 1 by 2 mod n now. So this is mod Pi, what do you get? Mod Pi, this is G raised to n minus 1 by 2, which is not G over Pi right. So A raised to n minus 1 by 2 is also not A over Pi, mod Pi. And what is A over Pi? Well, since for other j's A is 1 mod Pj, this is the same as A by n, right. So what you actually get is A raised to n minus 1 by 2 is not A by n mod n, okay, which leads to a contradiction. this will contradict B equal to Zn star. So then what this means is that this condition is true. So this condition is false. It's basically for every g and I, g raised to n minus 1 by 2 has to be equal to g over pi mod pi. Okay, this is what we have deduced. So let's continue with that. So assume that for all g, for all I, g raised to n minus 1 by 2 is the same as g over pi mod pi. Right? In the next step, now we will get a contradiction even with that. Okay. So we will use this to our advantage and get again a contradiction. So again pick an A such that A over P1 is minus 1 while A over Pi, or in fact let us just take the simple root, A is 1 mod Pi for I 2 to k for the rest. So A is a non-residue mod P1, but for the other PIs it is just 1. So by CRT, again by CRT pick this A. So by the red condition, what you will get is A raised to n minus 1 by 2 is A over P1, which is minus 1 mod P1, while it is A over Pi, which is 1 mod Pi. Right, so A raised to n minus 1 by 2 in Chinese remaindering is plus minus 1. For P1 it is minus 1, for the rest it is 1, which means that A raised to n minus 1 by 2 cannot be plus minus 1 mod n. Because if it was plus 1, then it will contradict mod P1. If it was minus 1, it will contradict mod P2. So here actually we are using the fact that there are at least 2 primes. Okay, this tells you that A raised to n minus 1 by 2 cannot be plus 1 or minus 1, which means that A raised to n minus 1 by 2 in particular cannot be A by n, which again contradicts. This is contradiction to B equal to Zn star. So which means that B is not Zn star. Okay. That's what we have shown. So we started with the assumption that B is equal to Zn star. That is what we assumed here. we started with this assumption, and we got n to be square free, and then we actually constructed either some G or some A in these two cases. Okay, that finishes the proof. So what this means that the probability is at most half. So let's write that down. The probability over A's of error is less than equal to half. Okay, so this is the first randomized polynomial time primality test with an elementary proof. Okay, so what next? So next we will just quickly we'll quickly remark that you can also ask the question whether there is a deterministic polynomial time algorithm for primality, and there is a way to de-randomize Solovay-Strassen also. So de-randomization of this can be done by something called Riemann hypothesis. So Riemann hypothesis is a conjecture in analysis, complex analysis. It's a very old conjecture. It also carries an award of $1 million. Our interest in that is, which was first shown by Ankeny and improved by Bach. So in the end, what you get is, they showed that if B is a proper subgroup of Zn star, like we had defined B to be the bad A's, and we showed that it's a proper subgroup, and a generalized version of Riemann hypothesis holds, GRH holds, then there exists a small a. One, two, up to 2 log square n. There exists a small a which is not in B. So what this is saying is that there will always be a small certificate. So if n is composite, then there will be a small certificate A, which you can find by just looking at the first around log square n numbers. So you don't need to pick A randomly. Okay, so this will immediately de-randomize the previous randomized test. So Solovay-Strassen can be de-randomized. Okay, that was a detour. So next we will study a more practical algorithm. a slightly more practical algorithm. Which was given by Miller, Miller was the first one to propose in 75, and Rabin made it probabilistic and practical few years later. Okay, this is the most popular primality test. So the idea of this is kind of taking square roots. So you had a to the n minus 1, then you took a square root of that, you got a raised to n minus 1 by 2. Now you take square root of this as well and continue. So then what you will get is a to the n minus 1 by 4, and then you will get n minus 1 by 8, and so on. So with high probability, we will see a square root of so either a raised to n minus 1 was not 1, in which case you already know this is Fermat test. So you will already know that n is composite. So let's start with 1. So you are basically taking square root of 1 every time, and with high probability you will see a square root of 1 other than plus minus 1. Proving that n is composite. Because if n was prime, then the only square roots of 1 are plus and minus 1, right. So that's the basic idea. It's already an algorithm, but let us anyways give the formal steps of the algorithm. So again, input is binary n. Steps are just the basic idea extended. So step 1 is same as Solovay-Strassen test, okay, which is either n is even or n is a perfect power, then you will output composite. Next step is randomly choose a. One to n minus 1. In fact, let me just say in Zn star, because otherwise if it is it shares a factor with n, then you factor n. That will be a certificate of compositeness. So randomly pick an a which is co-prime to n. Now if a raised to n minus 1 is not 1, then you will simply output composite. So let's assume it to be 1. So e raised to n minus 1 is 1, and compute Km such that n minus 1 is 2 raised to k times m, and m is odd. Basically 2 raised to k is the highest power of 2 dividing n minus 1. So compute these quantities, and then you compute the so called square roots. So for all I 0 to k minus 1, compute these square roots. So a m times 2 raised to I mod n. Now note that for I equal to 0, this is a raised to m. You can compute a raised to m mod n, then you compute a raised to 2m, a raised to 4m, and for I equal to k minus 1, this is a raised to n minus 1 by 2. Okay, so we are computing this square root thing, but in reverse order, starting from m and doubling it. So that will give you these ui's. And finally, check in the sequence of ui's, check for an anomaly, right? Square root of 1, which is other than plus minus 1. So if there exists an I such that ui is 1, but its square root ui minus 1 is not plus minus 1, then you will output composite. Else you will output prime. Okay, so only when you see a square root of 1 other than plus minus 1, you are saying composite, and you are correct. In the other case, you are just guessing prime, and we have to see the error probability. So again, since we are doing repeated squaring for a raised to m, and then we are doubling, this you can show is doable in log square n. So the time complexity is O tilde log square n. Okay, so this is definitely polynomial time. In fact, it's very fast. Like Solovay-Strassen, it's quadratic time. The first observation is as before, that if n is prime, then it outputs prime. Why is that? Well, as I already said, 1 has only 2 square roots modulo a prime. Square root of 1 is only plus minus 1. There cannot be a third square root, since Z mod n is a field. Okay, because of that. So step 4 cannot say positive, and in the previous steps 2.1 also cannot say composite, because a raised to n minus 1 will be 1 mod n by Fermat's little theorem for any a. So, and step 1 also cannot say composite. Okay, so the main thing that we have to show and analyze is what happens when n is composite, and this algorithm outputs prime. What is the chance of that? So if n is odd and has at least two distinct prime factors, okay, which is being checked already in step 1. So suppose n is odd and there are at least two distinct prime factors. Then the bad is that is in Zn star for which the test is failing. I mean, test is failing as in for which the algorithm is saying prime, right? So for them e raised to m was 1, which means that all these UIs they were 1, or somewhere -1 appeared, and after that sequence of ones. Okay, so this is the set B. The bad is, so either all the UIs are 1 or the sequence of UIs have somewhere there is a -1. Then the test will say, algorithm will say prime, although n is not prime. So the bad A's are at most phi n by 4 many. Okay, so the bound that you will get here is slightly better than Solovay-Strassen. There you had phi n by 2, here phi n by 4. So the probability of error is even smaller, it's 1/4. Right, so there is a 75% chance of success. So give it composite in the input, it will output composite. Prime, it will obviously output prime. So let us try to prove this of it now. So again we'll use Chinese remaindering on n. So note that this B, this may not be a subgroup of Zn star. Right, this may not be a subgroup because -1 times -1 becomes 1. So that is a problem. So we'll actually first identify a subgroup and then analyze that. So let us to move in that direction, let us say 2 raised to L, let this be the highest 2 power that divides all the p minus 1s, prime p Okay, so let 2 raised to L divide each of these. Since n is odd, p is odd, so p minus 1 is even. So let 2 raised to L be the highest power dividing all of them, and then define a different set B prime, we will call it, which will contain A's such that A raised to m to L minus 1 is plus minus 1 mod n. Okay, and the advantage of this A is that it is a subgroup. So B is a subset of B prime, and B prime is a subgroup of Zn star. That is the advantage. Okay, so we have identified actually a bigger set than B, and it is a subgroup. So we will now actually show that B prime, hence B is small. So this subgroup B prime, how big is this? Okay, let us study this. In fact, first of all, why is it a why does it contain B? That is an important proof. So B prime is clearly a subgroup. That is not the problem. Problem is why is B contained in B prime? So let A be in B, which means that either A raised to m is 1, or there exists an I such that A raised to m 2 raised to I is minus 1. Now, if A raised to m is 1, then A is also in B prime, because the definition of B prime includes that A raised to m1, right? A raised to m1 would mean that A raised to m times 2 raised to L minus 1 is also 1. So that's a done case. So let us assume that A raised to m 2 raised to I is minus 1 mod n. So this means that for all primes P that divide n, in fact prime power P dividing n, A raised to m 2 raised to I is minus 1 mod P raised to E. Now let us again invoke this property that Z mod P raised to E star is cyclic of order phi P raised to E. So since it is cyclic, what can you say about P minus 1? So you know that A raised to phi P raised to E is 1 mod P raised to E, right? And one thing more you can write, which is obvious, that e raised to m to I plus 1 is 1. So, you know these three things. You know that m 2 raised to I is minus 1, hence you know that m 2 raised to I plus 1, so square of the previous thing is 1, and you know that this group z mod p raised to e star has size phi of p raised to e, and it is a cyclic group. So, a raised to that is 1. Now, from these three conditions, what can you, these three properties, what can you deduce? Okay. So, we deduce that 2 raised to I plus 1 divides p minus 1. So, p minus 1 is the only even part of phi of p raised to e, right. Suppose something smaller than, suppose 2 raised to I plus 1 does not divide p minus 1, only 2 raised to I divides, okay, the highest power is only 2 raised to I. So, in that case, e raised to m 2 raised to I should have been 1 as well. Okay, so, if you look at this third property, this tells you that 2 raised to I plus 1 is necessary and sufficient to get 1. Okay, so, p minus 1 has to be divisible by 2 raised to I plus 1. And once you deduce this, you are good, because now I relates to L, right. L was the 2 raised to L was the highest 2 power. So, it means that I plus 1 has to be less than equal to L, which means that I is less than equal to L minus 1. Okay. So, now since already you have this green property, a m to I equal to minus 1, you learn that a raised to m 2 raised to L minus 1, which is at least I, this value will also come out to be plus minus 1. Okay, that is what you deduce. And this means what? This means that A is in B prime. Okay, so B is a subset of B prime and B prime is a subgroup. So, that is something very good. Now, let us move to the size. So, how large is B prime? Okay, so we will show that, first we will prove a structural property, that size of B prime is 2 times the product over all the primes dividing n this. Okay, basically it's we are multiplying over the primes p dividing n. For a prime p, we have this GCD times 2 raised to L minus 1 number. This may seem very mysterious. It will actually follow from we will follow Chinese domain ring theorem to get this. First, analyze or estimate the number of A's such that AM2L minus 1 is 1, and then we will estimate equal to minus 1. These are the two options, right? So what is this? This is, let's go over different primes. And do Chinese remaindering. So this will be A mod P raised to E star. How many A's are there in this subgroup? This is a subgroup of Z mod n, Z mod n star, right? So we are doing Chinese remaindering. So how many A's are in this such that A raised to M2L minus 1 is 1 mod P raised to E, product over this number. Here it will be important that Z mod P raised to E star is cyclic. So this number will come out to be basically think of a generator of Z mod P raised to E star, and it will have order phi of P raised to E. So take the GCD of this with phi of P raised to E. So generator G has order phi of P raised to E. How many powers of that will give you such A's? That's the question. And you will get it by taking the GCD with M2 raised to L minus 1. Okay, you can show this as an exercise. Since this is cyclic. So that is why this is a very precise estimate, which we can further simplify. So now we take product of primes over n, primes dividing n. So you get GCD of M2 raised to L minus 1 and P raised to E minus 1, P minus 1. Well, P is co-prime to both M and 2. So this can be dropped. P raised to E minus 1 can be dropped first. And next thing is what to do with 2 raised to L minus 1? Does it divide P minus 1? Yes, so in fact 2 raised to L divides all the P minus 1s, right? So 2 raised to L minus 1 divides P minus 1, so we can further simplify this as this. Okay, so we have estimated the number of A's such that A raised to that exponent is 1 mod n. Fine. How many of these will be minus 1? So the -1 number actually will also come out to be the same. So we just have to double this. So overall we deduce that the size of B prime is twice what we just calculated. Okay, so that's the expression. Now let us look at the ratio of this B prime size with phi n. What is the ratio? So phi n can also be factored over the primes. So what you will get is 2 raised to L minus 1 times the GCD of m and p minus 1 in the numerator, and in the denominator you will get p raised to e minus 1. So we are actually doing it over prime powers. Prime powers that exactly divide n. So since m is odd, note that m comma p minus 1. So m comma p minus 1 times 2 raised to L minus 1 will divide p minus 1 by 2. Because p minus 1 by 2 is divisible by 2 raised to L minus 1, okay, which is all that appears in numerator. 2 raised to L minus 1 appears, the remaining part is odd. So this part is odd. So hence the numerator divides p minus 1 by 2. So which means that so it is smaller than p minus 1 by 2. Right, so since the numerator is smaller than p minus 1 by 2, we actually get an estimate of this. We put half here and p raised to e minus 1 here. Okay, so we will proceed in the next class. Okay, soon we will get that this number, this you can see that it seems to be quite small. We'll just have to look at some cases and actually formally prove that in all cases it is less than at most 1 by 4.